Welcome to the second module of the course, Analysis of Several Variables. So in this second module, we are going to study the linear applications from Rn to Rm. In this chapter, we are going to cover 6 sections. So first section is linear functions. Second is the associate matrix of linear functions. Then we have here the third is the norm of linear functions, then ridge representations theorem, and the last theoretical topic is adjoint of linear functions, and then we have the numerical problems associated with all those 5 topics. We'll discuss it in the end of the chapter. So let's start with the linear function. So we say that A is from Rn to Rm is a linear function if Ax plus lambda y can be written as Ax plus lambda ay, and we denote it as A belongs to L, Rn to Rm. So this is the conditions for the linearity of a functions from Rn to Rm. So in this case, we have x belongs to Rn, y also belongs to Rn, and lambda is a real number. Then by the properties we know that x plus lambda y, so this is belongs to Rn, and same way Ax and lambda ay, which are belongs to on Rm. So therefore the linearity conditions is given by this equation. Okay, now we note about few properties of A is from L Rn to Rm. The very first property is that A0 is equal 0, means that 0 of Rn will go to 0 of Rm. So the function here mean is that 0 of Rn will goes to 0 of Rm if A is linear. It's guaranteed that 0 goes to 0. Okay, so that means if let's say n is equal 2, m is equal 3, then 0 0 will goes to 0 0 0. Now how we can verify these properties? So we can prove it by contradiction. So let A0 is not equal 0. Now we can write this is as, this can be equivalent to A of x minus x is not equal 0 for all x belongs to Rn. Now since A is linear, we can write it as Ax minus Ax, which is not equal 0. This is because A is linear. So this implies Ax is not equal Ax. So this means that the same image by A are not equal. So which is not possible, a contradiction, which is a contradiction. So therefore our assumptions was wrong and we got A0 is equal 0. This is the proof of this fact. Okay, now this is just a note to understand it, that if we have the linear combinations of several vectors like this up to p vectors, then it can be separated for all. So lambda 1 can be the scalars can go out and the vectors can be separated due to the linear property of A. Okay, now we have another interesting definition is one is that kernel of A and another is image of A. So what does it mean kernel of A? So let's you have here Rn and here you have Rm. So this is 0 Rn and this is 0 of Rm. So it's guaranteed that Rn will goes to Rm by A. But if some other entries, if say other entries goes to 0 of Rm, so this entries, all entries are goes to Rm. So this is x1, x2, x3, x4. So therefore, in this case, kernel of A will be all those entries which take the entries elements to 0 of the other space. So therefore, in this case, it will be 0 Rn, which obviously goes to 0, and x1, x2, x3, x4. So these are the all entries goes to the 0 of Rn, and they are known as the kernel of A. So therefore, the definition says that kernel of A is all x belongs to Rn so that Ax equal 0. So therefore, you can see that kernel of A is belongs to uh, from the entries of Rn. So therefore, we can know that kernel of A is subset of Rn. So therefore, kernel of A will be a subspace of Rn. We are not going to prove that it is subspace. It's obviously true if you check it, use the definition of subspace. So kernel of A is always subspace of Rn. Now next one is that image of A. Image of A is that, so you have here Rn and here Rn. So therefore, all the entries of Rn will map some point in Rn. So this is 0 Rn. This is obviously goes to 0 Rm. But other entries, all the entries have a map here. Now, some entries maybe go to the same point. So therefore, the collection of the points in Rm is known as the image of A. Means where the points of Rn are is going, that's the image of. So therefore, that's why Ax and x belongs to Rn. So whatever you choose the x, you will go to Rm, and those points is known as the image of. So clearly, the image of A is a subset of Rm. So therefore, it will also be a subspace of Rm. Okay, so this says that dimension of the kernel of A and dimension of the image of A will be dimension of Rn, which is equal This is always true. Okay, now how we'll get a linear combinations of linear functions. So how we can define that? So let's AB belongs to L Rn to Rm and lambda is any real number. Then A plus lambda B, the linear combinations of the linear functions A and B is a functions from again Rn to Rm, and it's defined as like this: X is belongs to Rn, then A plus lambda B x, this is equal Ax plus lambda B. So if this function is the linear combinations the of the functions, which is again be linear. Okay, so now another definition is composition of linear function. So if A is from LRn to Rm and C is from Rm to Rq, then the compositions of these two linear functions, C composition A is given as Rn to Rq. Basically, C will be defined from C will be different from the image of Rn by A. So therefore, we will have here, we can take it like this. So this is Rn, this is Rm, and this is Rq. So we have here Rn, all the entries will go to some set of Rm. So this is let Rm. So therefore, C is defined from there. So this one is A R N, which is subset of R n, and C should be defined from in this, not from whole Rm. So C is defined from here. This is C, this is A. So therefore, C is defined from this subset of Rm, which is mapped by Arn. So in this case, then it will be whatever it is that will be there. So therefore, this whole mapping is, whole story is known as the C composition A. So this is the definition. And C composition A, how it will define? C operating on A, which is operating on X. Okay, now this is a basic definitions of any functions. So when we say that fx to y is a function, then we say that this function is 1 to 1 if and only if for all x1, x1 belongs to x, f of x1, f of x equal f of x1 implies x is equal x1. So this is called 1, 1. Onto is that from the domain set y and from x, if you choose any y here, automatically you should have some entries in x such that x y is equal f of x. If for all y there exists an x in x such that y equal fx happen, that is called on to. And bijective, if it is 1 1 and on 2 always, so then it is known as the bijective function. So if it is bijective, then it is invertible, and f inverse y is equal x if and only if y equal fx. So therefore, if it is bijective, then x will goes to y, each x goes to separately. Then we call it is invertible, and the invert function is given like this f inverse y equal x. Okay, now in this proposition we have if a is from Rn to Rm a linear function and a is 1 to 1 if and only if ax is equal 0 implies ax is equal 0. Now just recall about the kernel. So what is kernel of a? So you have to get all the x belongs to Rn such that ax is equal 0. Now, in this case, it says that if a is a linear function and if a is 1 to 1, then ax equals 0 implies x equals 0. So, this means in this case, kernel of a will contain 0 entries. So, if a is 1 to okay, so let's have the next. Okay, now we have a theorem here. This theorem says that if A belongs to L Rn to Rn, so this is we have to be careful on that. The definitions how it says that here it is not saying Rn to Rm. It is saying that Rn to Rn. So it should go to the same space Rn. Then we can talk about this bijective 1 1 and on to equivalency. Okay, now if we want to prove that, how we can prove it? So first is that let A is bijective. So if A is bijective, so this implies A is 1 to 1 and A is also 1 to. So this is true now that if they are bijective, then both are. Now next one is that if the important thing is that if A is 1 to 1, then what will happen? Okay. Now let's say A is 1 to 1. Let A is 1 to. So this implies kernel of A is only contained 0. So therefore, dimension of kernel of A is equal 0. Now by the properties we have that dimension of kernel of A plus dimension of image of A is equal n. So if it is 0, so this implies dimension of image of A is equal n. So this is possible only, this implies A is 1 2 because image and the image set and it will be same as the dimension of the range set if it's if the function is onto. So therefore A is onto. Now this is we can reverse it. So we can have if and only if and only if, and this is also means you can say the reverse way that it is dimension of kernel of A is equal 0. So therefore kernel of A is 0 and A is onto. So therefore all three conditions are equivalent with each other. So you have to remember here this is true only for A is from Lrn to Rn. Any other cases, it may not hold good. Okay, now next we have another interesting definition, which is that invertible. So a linear functions from a Rn to Rn, we say that it is invertible functions, and we denote it as a l inv Rn. So this inv is known as the inverse. If and only if a is onto and 1 to 1 linear function. So since a is onto and 1 to 1, it will gives you the bijective. So it is automatically holds good. So therefore we can conclude that A belongs to L inverse Rn if and only if A is a linear function from Rn to Rn and is bijective. Then we call this function is invertible. Okay, so this finishes the section 1 of module 2. Now we move to the next sections, which is the associate matrix of a linear function. So we have a theorem here, and it says that for all A belongs to L, Rn to Rm, there exists a unique matrix A from m by n. So therefore, the order will be m by n of the matrix, such that for all x belongs to Rn, Ax is equal matrix Ax. So therefore, every linear functions can be written as a matrix form, and this matrix A is known as the associate matrix of the linear transformation A or linear function A, and the order of the matrix is m by n. So therefore, if A is from R2 to R3 and A belongs to L, R2 to R3 means linear, then the matrix A will be 3 by 2. We will do one example where we will try to find the matrix form of the function. And first we will show that that function is linear, and then we will show that we will find the matrix of this linear function. So let's have the solution here. First we have to show that A is linear. So therefore let x is equal x1 x2, y is equal y1 y2, and then x y both are belongs to R2. Okay, then for lambda belongs to R, we have x plus lambda y. So this will be x1 plus lambda y1, x2 plus lambda y2. Now we apply on this to the function, so we'll get it a x plus lambda y. So this is equal a x1 plus lambda y1, x2 plus lambda y2. So now we'll apply the linear functions here. So this linear function is defined is like this. So be careful how to apply it. So here is x1 x2, that means first entry is, here is first entry is, then x2, and this is 3x2. So therefore multiply of 3 of the second entry. So in this case, what is the first entry? X1 plus lambda y1. So it will be as it is, x1 plus lambda y1, and then we have 3x2. So we'll have 3x2 plus lambda y2. Now same way, it is 2x1 minus 2 minus x2. So 2x1 is to x1 plus lambda y1 minus x2 plus lambda y2. And third one is x2. In this case, it will be x2 plus lambda y2. Now we'll separate the part which is associated with lambda and without lambda. So therefore, we can rewrite this as x1 plus 3x2 plus lambda y1 plus 3y2. And this one will be 2x1 minus x2 plus lambda y1 minus lambda 2y1 minus y2, and third one is x1 plus lambda y2. So this we can separate it as x1 plus 3x2, 2x1 minus x2, and x1 plus lambda y1 plus 3y2, 2y1 minus y2, and y2. Okay, so this is nothing but ax plus lambda a y. So this implies a is linear. So this implies a belongs to L R2 to R3. So now what is the next? To find the matrix of A. So again, if you want to rewrite it, the linear function, so it is given as ax is equal x1 minus 3x2, 2x1 plus 2x1 minus x2 and x2. So this is here. So now this is we can rewrite as 1 minus 3, 2 minus 1, and 1, 0, x1, x. So this is nothing but a matrix A and x. So here A is equal, the matrix A is equal 1 minus 3, 2 minus 1, 1, 0. And as expected, since A is from R2 to R3, the matrix should be should be 3 over 2. So which is true, that the matrix is 3 over 2. Now we have some basic properties of associate matrix. So here you have if AB belongs to A, L, Rn to Rm, okay, then A plus lambda I, we already defined this linear combinations of the linear functions. This is also belongs to L, Rn to Rm, and the matrix of A plus lambda B is or can be separate, and it is can be written as matrix of A plus lambda matrix of B. And same way, if A is from Rn to Rm and C is from Rm to Rq, if means Arn is subset of Rm, then we can define the compositions, and the matrix composition, C composition A matrix will be matrix C multiplies matrix A. You have to keep the order of the matrix in sequence. So first C, matrix C, and then the matrix A. So how we can prove this part? So we are going to prove this both statements. So let's start with the first part. that A plus lambda B is linear and its matrix will be given by as it is written here. Okay, so let D is equal A plus lambda B, where AB belongs to AB belongs to L, Rn to Rm, and XY belongs to Rn, and lambda belongs to R. So then if we apply there, so D of X plus, so we will take here alpha belongs to R. So X plus alpha Y. So what is means here? Because we have to show T is linear. So to prove that, we have to show it that this is equal dx plus alpha dy. So ax plus alpha y. So this can be a plus lambda b and then x plus alpha y. So therefore, since this definitions of this linear combination says that we can separate them. So x plus alpha y plus lambda b x plus alpha y. Now what are A and B? A and B are linear. So therefore we can write it as this is equal ax plus alpha ay plus lambda bx plus alpha lambda by. So since A and B are linear, A, B are linear from Rn to Rm. So now what we will do, we will take it separate way and then we will see how we can write it. So this can be written as ax plus lambda bx plus, here we take out alpha, then you will have ay plus lambda by. So this will gives you a plus lambda bx plus alpha a plus lambda by. So this implies this is dx plus alpha dy. So this implies d is linear from Rn to Rm. So we prove that the linearity part. And now we'll write the matrix form. Okay, matrix form is obviously true, but we can also write it in this way, that what is the matrix form definition? So we'll have D of X is equal matrix of D operating on X. Ax plus lambda Bx. So this is, we can, if you want to write in a matrix form, so this will be matrix of A operating on X plus lambda matrix of B multiply X. So this is equal, can write it as matrix of A plus lambda matrix of B multiply X. So now we already saw that this is, so this implies dx is equal A plus lambda b. So since this is we can say left hand side and this is right hand side. So if you combine them, so this two will gives you A plus lambda b matrix is equal matrix of A plus lambda matrix of B. So this will gives you the summation. So now we are going to prove for the composition. So let for part B, let E is equal C composition A, and as in the last problem, x y belongs to Rn, and we say alpha belongs to R, and then we will have E x plus alpha y. So this is equal Ex plus alpha Ey as in the last problem. Definitions what we can get it there. So now so we take the left hand side. So let Ex plus alpha. So what is E here? E is equal C composition A. This is equal C composition A x plus alpha y. Now by definition of the composition, what you will get it? C A operating on x plus alpha y. So now since A is linear, we'll get it C. This will be AX plus alpha A. So this together will gives you C operating on AX plus alpha C operating on AY. So this is nothing but C composition A x plus alpha C composition A y. So this is the left hand side, and same way the right hand side. So this is left hand side. So right hand side we'll have Ex plus alpha Ey. So this will gives you C composition A x plus alpha C composition A y. So therefore left hand side is equal right hand side. So therefore the C composition A is linear. So this togetherly will gives you C composition A belongs to L Rn to Rn. So now we have to show that this two are the matrix form of this composition. Okay, so C composition X. So for the matrix form, we will have here C composition A X. So this is, we can write it as C operating on AX. So therefore this will be matrix C AX. Now AX, it will be further. So this is matrix C and this is operating on AX. So C composition A is equal this one. Now again C composition A X, its matrix form written as C composition A X. Now comparing these two, you will get it C composition A is equal matrix C multiply matrix Let's complete the. Now we have a theorem here. Associate matrix of invertible function. So says that let A belongs to this theorem statement is there. Let A belongs to L Rn to Rn. Then A belongs to L inverse Rn. If and only if and only if the matrix A is invertible. The matrix A is invertible and A inverse belongs to L inverse Rn, that is inverse function is also invertible, and the matrix A inverse is equal A inverse of the matrix. Okay, so we know that A is have an inverse if only if A is bijective. So therefore, the matrix form is also invertible if determinant of A is equal 0, not equal 0. So a matrix is invertible. A matrix, just recall, A is invertible, or let's take same notation, if and only if determinant of the matrix A is not equal 0, and which is also the bijective of linear function. Let's have an examples which use this theorem. So let's A is from R2 to R2 is defined as AXY is equal 2x minus y and x plus y. So we have to first find that A is, so we have to find that, prove that A belongs to L inverse R2. Part B is find the matrix of A inverse, and C is find the inverse image. Find the function inverse image. So how we can do this one? So in this case, we will have first solution. Okay, so we can do it two method, but we will take the here easy one, which is in the matrix form as in the previous theorem. So AXY is given as 2x minus y, x plus y. So we just to make it easy, we convert this one in the column form so that we can write matrix easily. So this can be written as 2 minus 1, 1, 1 and x, y. So therefore, the matrix form of A is equal to minus 1, 1, 1. Now, what will be the determinant of A? So determinant of this matrix A is equal to minus 1, 1, 1, which is 2 plus 1 is equal 3, not equal 0. So this implies the matrix A is invertible, and which in turns by the previous theorem that A belongs to L inverse R2. Okay, so now the question is here, find the matrix of the A inverse. Okay, so here the second part is that matrix of A inverse. Again by the previous theorem, this is equal matrix A and then its inverse, because matrix A is known to us and the determinant of the matrix A also 3. So therefore this inverse will be 1 over 3, and the 2 by 2 matrix is just change the position of these two, so it will be 1, 2, and change the symbol of this one, so this will be 1 and this is minus. Okay, now third part is that it says that find the image. So what is the image of this? In this case, what we have to do, we have here A inverse. We have to find the A inverse actually. So A inverse, so this will be also from R2 to R2, and it says that if it is UV, then what will be this structure when you define on this function. So that is our finding is A inverse UP is equal. So again we will try to write it in the column form to make easy calculation. Okay, so if we take W is W is equal UV, which is belongs to R2, then the matrix form of this A inverse W is equal A inverse W is equal matrix of A inverse W. So you already know the matrix of A inverse, so which is 1 over 3 minus 1 over 3 2 over 3, and W is UV. So therefore if you combine them you will get it U plus V over 3 and minus U plus 2V over. So therefore we got it A inverse UV is equal U plus V over 3 and minus U plus 2V over. So this is one method. We will get all the answer here. And you can also have another method to solve this question. So first one is to show that. So second method, you can adopt any one method. The matrix one may be the easy one, but some cases the second method also be easy. So A belongs to L inverse R2. So to prove that, so this should be if and only if A is bijective. Okay. So which is equivalent to equivalent to kernel of A is equivalent to 1 1 1 2 1, that is kernel of A is equal 0. Okay, now again we recall what is A. AXY is equal, let's go back and check it. AXY is equal to 2x minus y over x plus y. So 2x minus y, x plus y. So we want to try to find the kernel. So this will be 0 0 if and only if 2x minus y is equal 0, x plus y equal 0. And solving this, we will get x equals 0, y equal 0. So therefore, kernel of A is contains only 0, 0. So therefore, this implies A is 1 1, 1 to 1. This implies A is bijective. This is the first part of this theorem, and so this implies A belongs to L inverse R2. So image, how we can find it. So we have to find it here. Let's A is from R2 to R2. So this will take you XY to U. Now the question is, so this is A. So now the question is, what will be A inverse? So A inverse UV, how we can write it in the form of the X and Y. So from this first definitions, you know that UV is equal A X Y. So this is nothing but with as per definition. So this is 2x minus y, x plus y. So therefore, if we compare it, we will get it here. 2x minus y is equal u, x plus y is equal v. So therefore, if we solve them for x and y, we will get it is in terms of u and v. So therefore, what we will get it here? If you solve them, okay, add them, you will get it here. 3x is equal u plus v. So this implies x is equal u plus v over 3, and y is equal v minus x. So this is equal v minus u plus v over 3. So this is equal minus u plus 2v over 3. So therefore, we have there A inverse uv is equal xy. So this implies A inverse uv is equal x in terms of v is u plus v over 3, and y is minus u plus 2v over 3. So this you will get the image of A inverse.